welcome. Thanks for joining, and let's go. Before I start with the topic, let me quickly introduce myself. So my name is Jakob Löhnertz. I was born and raised in the beautiful Rheingau region of Germany. Next closest city would be Frankfurt, which I guess you all know. And I moved here to the Netherlands about 4 years ago. I'm a tech lead at Picnic, the online supermarket, who won the Innovation Award last year. Actually, I worked on this project, but moved on to another role recently. And please see us here at our booth, pretty much in the middle of the bottom floor, if you want to know more about what we're doing or you're looking for a job. You cannot really miss it. We have this big vehicle which we deliver our groceries in. Outside of work, I'm running an educational YouTube channel, which is about software engineering. You can see the name here on the left-hand side. Check it out if you want to. There's quite some Kotlin content, but also other stuff. It's a bit hard to find, so I think you have to like append channel at the end, because, well, it's not that many subscribers. You can change it, I guess. Apart from that, I'm coding. Yeah, there's this weird glitching going on. I'm not quite sure why. The AV expert is neither. I'm coding on stuff outside of work that has nothing to do with work, so quite some hobby projects. I'm into all things remote controlled, specifically cars and multi-copters. I watch and follow like a very large variety of sports, and myself I'm practicing bouldering, snooker, and darts. But that's not what you're here for. You're here for Kotlin. So first time I used it, the thing that sort of drew me into it is just this exact set of, well, not that exact one, but the amount of features and this combination of features that it offers that in this combination, at least, I feel I cannot have in any other language. And then I looked more and more into it and wondered, it's pretty soon, because the common target platform, of course, is the JVM. How can this possibly work? Because there's like a lot of features that Kotlin offers that you will not find in Java. It gets better and better every release of Java, of course, but still there's some that it will probably never have and historically didn't have. And it got me curious how that can possibly work. Here you see a very, very simple example. One of the sort of big common features, the nullability that Kotlin offers that commonly, as you know, Java does not have. Everything is nullable apart from primitives. So we have very simple setup here. It's just a stupid constructor that accepts a number. So if you're not super familiar with Kotlin, if you want, this does not accept a null value. Otherwise, it would have to be a number question mark. And then we have a toString method. Well, that doesn't do much. But then I wondered, since Java JVM doesn't know about non-nullable types, every object is nullable, how does it A, represent this, sort of convert this to run on the JVM in bytecode, and B, how does it make sure that the feature is correctly enforced if I would use this from within my own Kotlin application? Yeah, so we're going to find that out today. So welcome to Dekompiled, where we'll be analyzing how Kotlin's features are represented on the JVM. Right. Quick agenda, what we're going to do. I'll start with very quick introduction to the topic. I'll keep it light, but I don't want that anyone sort of completely checks out for the rest of the talk. But the majority of the focus is precisely what I just said, how Kotlin's features are represented on the JVM, so sort of the compilation step. And then secondly, how they are enforced, that they work according, well, to what the language specification of Kotlin says. Which, as you might imagine, can be a bit difficult since there's not clear sort of equivalence in JVM oftentimes. Right, let's start with sort of how does the Kotlin compiler work on a very, very high level. It's Kotlin C, and as many compilers, first step would be the compiler front end. So you dump in your still human-readable Kotlin source code, and the front end typically takes care of parsing this apart into a bit more abstract representation and doing analysis on it in the sense that yeah, obvious language features are sort of used correctly, and it would then fail, of course, in this step already. So there's this obvious things such as typing, right? If you, in this example, it wants a number, the constructor. If I give it Boolean, the front end will give me some error message. It doesn't even continue with the later stages. But of course, it also takes care that the features that Kotlin specifically have, that is not necessarily JVM specific, since, of course, there's other target platforms, that this is respected and done correctly. Otherwise, it fails there. The next step then, this was added some time ago, by now, quite some time ago to Kotlin, is that it converts this to a more abstract, even more abstract representation, or called intermediate representation, short IR. The idea here is that because Kotlin has not just the JVM as a target platform, they sort of want to achieve that They don't have to swap out half the compiler every time if you target different things, but instead we sort of take away Kotlin from its very Java-y, Scala-y nature that it has, of course, to a more intermediate, well, abstract representation, such that then the step to all the final target platforms is smaller, if you know what I mean. So that's what happens here. They will revamp this a bit with K2, the new Kotlin compiler that is currently in alpha, if I'm not mistaken. So it will change a bit, but the general structure, as far as I'm aware, at least, will stay the same. The other thing that does happen here is some IR-based optimization. So obvious things you would expect from a compiler. It figures out, I don't know, that you some branches of your if conditionals can never be reached or always true, whatever, this kind of stuff, and it sort of optimizes that away before going to the target platform. And then the final step, unsurprisingly, the compiler backend. Here we do some more optimization for exactly the target platform. So these are sort of the most three common ones. There's other ones being added to Kotlin. So what happens here, what I mean by this is stuff that will make your code run fast or memory efficient on the JVM are, of course, different optimizations that work well on, let's say, V8 for JavaScript. So here's like a target platform specific optimization that you can only do at this step, because then you sort of know that. And then the other obvious one, the actual code generation, such that we receive JavaScript, JVM Bytecode, JVM Bytecode, also known as native platform, or WebAssembly, as they also have an offering. Of course, today we're going to focus only on the JVM Bytecode, since, well, we're at J4. Right. Let's move on then to, this is probably obvious to most people, but I want to point out that this is an important thing to understand for the remainder of the talk. So the thing that Sun and Oracle and so on have been advertising, of course, all the time is that Java is so portable, right? Because you have this also some sort of intermediate representation that is the JVM bytecode that you can then run on any JVM as long as it's according to spec, as it's legal or whatever. What that means, of course, for the JVM then that runs this is that this doesn't know, obviously, anymore what is it actually running. So it obviously was designed originally, as the name implies, for Java. But as long as I give it legal JVM bytecode, it will just happily run stuff and other stuff as well. So keep this in mind. Importantly, the JVM, that cannot know anymore once it runs this bytecode, am I running Java here or Kotlin, or of course also some mix, right? One other big feature of Kotlin, interoperability. I think Scala also has this in their latest version. You could have a combined code base, half Scala, half Kotlin. I was to say half Java, the third stand at that point. So keep that in mind. And when I wanted to look a bit deeper then into answering these two questions I had, how is this represented and how is it enforced, you obviously very quickly have to look at JVM bytecode. No worries, this is the only slide in the whole presentation that will contain any bytecode. I'm also by no means a big expert on this. But the problem here, of course, is that this is the toString method you saw earlier on the first slide. That's quite readable. You can, if you look into this a bit, or if you're knowledgeable with it, it's okay. You can sort of read it as a human. Of course, usually it's binary format, but most JREs have tooling to get it into this human readable format again. But it's still a bit tedious, right? If you would have a larger example, this toString is pretty stupid. Nothing much happens. This A gets very long and also pretty difficult to read. So I figured, this is not great to study a bit of more examples than just one. But the other thing you notice here, of course, is that it's also important to keep in mind, obviously, the JVM bytecode spec and Java were designed sort of together in one cycle. So you recognize here, of course, a lot of keywords you would know from Java as well that are very present in JVM bytecode as well. So it's a very sort of, they share a lot of ideas and things. I guess that's fairly obvious. So what I did then to answer my two questions is I looked into all sorts of Kotlin features and analyzed them. So these are all the ones I took a look at, which are pretty much all of the all the ones I could find, at least stuff that is not super obviously present in Java as well. Some stuff by now Java has as well, of course, but important also here to keep in mind is that by default still the Kotlin compiler, if you do not change it, compiles to Java 8 bytecode. So it cannot even use the newer features, so they still sort of, that's important to keep in mind. yeah, what I did then is sort of this methodology right here. So I wrote a small snippet for each of these features you saw on the previous slide, which are around 40, I think. Uniquely only using that one feature. I tried to, the code is stupid, doesn't do anything useful as you saw, but yeah, exhibits sort of the one feature at a time. And then I compiled this, in my case, Kotlin C version 1.6.0. It's a bit older, but back when I did this, but should make a big difference, to then get the JVM bytecode. And then I thought, because, well, it's, as I said, a bit tedious to analyze, but JVM bytecode is very, very similar to Java in many regards. Hey, there's a lot of decompilers out there. I'm sure most of you have used it. Most IDEs ship with one, or you can install it, to get from JVM bytecode back to Java, for instance, to look at how a library is implemented without having the source sets available. I played around with a few of them, and the one I settled on in the end is CFR version 0.152 that yielded the best results. So the idea being here that because JVM bytecode and Java are pretty similar, at first I was like, it's probably not going to work, but actually this yielded very good results. So if you sort of pipe it, each snippet through this methodology right here, in the end you get Java back, which you can, apart from one example where it really, really doesn't work, which is the suspend keyword, for everything else, you can very clearly see, oh, this is how they sort of, under the hood, the Kotlin compiler, what sort of trickery it does to achieve its features to be present in JVM bytecode, because most do not have a clear one-on-one mapping. Keep in mind this is not perfect, because of course at some points the decompiler has to do some guesswork, because there's some information just lost in the compilation stage, both for Java and Kotlin. So the code, no human would write it that way. It looks really ugly usually, but it's still pretty readable. You can, from almost all examples, pretty clearly sort of see what's going on. This is of course not as perfect as just looking at the bytecode, but I guess you see my point. Right, then let's move on to how Kotlin's features are represented on the JVM. Right, so if we look at the example again from the beginning, this very stupid class that uses non-nullable types, how this would look in once run through this pipeline I showed you on the previous slide is something like this. This is not super surprising. We're going to get to a bit more interesting examples later, but you notice a few things here. So the first one is it obviously compiled my field in there, which in Kotlin was just this val notation that it's constructor and field declaration in one. So I have a private final number. Importantly, of course, this is a nullable number, right? So there are no non-nullable types in Java 8 at least. So this is a nullable number. So what you also notice, it added these org.jetbrains.annotations package annotations, not null, which Java also has, in 3 places. So you see it on the field, on the constructor argument, as well as on the return type of the toString method. So there's also a non-nullable string that returns. So the other thing you notice is that it synthetically added this check here with the intrinsics. So this is from Kotlin JVM internal. So I guess the name implies it's not meant for use in your code. It's pretty much like require non-null in Java. So it's intrinsics.check not null parameter. So this would check if what is received here is null, and if so, throw an exception so it at least fails fast. So this is good to keep in mind. So if you think about how is this represented, well, actually it's just represented as a nullable type, but because they don't really have any other choice. And then it, at least at, of course, this is not great, but at runtime in this case, then it would enforce to at least throw this exception, such that sort of the remainder of the class where you would expect it to be non-nullable, in this case just toString method, but obviously usually a bit more useful code, the class sort of is still correct. So what you then find, if you look at all the other examples, is that typically the compiler has then two options to represent the language feature. So either they solved it via the compiler frontend. So stuff to just make sure that in the compilation stage of Kotlin already this fails. That has to be made sure as well in this case, of course, where we do have this annotation. That's actually not how they do that, as you'll see later. But there's a lot of things where it has to make sure, where statically, so to say, can make sure that the language feature is correct. And then the other thing it has as an option is to use the backend. So during this code generation step, to sort of synthetically add stuff into the bytecode that is not visible or present in your human readable Kotlin code. Mostly, yeah, for these reasons, to at least fail at runtime as fast as possible, to not get into any weird situations to begin with. Right, then let's look at how Kotlin's features are enforced on the JVM. So if you look at something like this right here, which is the field in the end that it compiles, right? As I said, this is still a nullable type, right? This is not non-nullable. So let's imagine this example right here. We have a Kotlin library distributed as a jar. So we just have the bytecode, no source code anymore. We can, of course, now use this from within our own Kotlin application or from Java, right? So the issue here is then, if you think about not how it's represented, but how is this enforced that the feature works correctly, how can it make sure that even though the type is nullable in Java, that if I would call this constructor from my Kotlin application, it still fails in the front end, right? The compiler front end would still scream at me if I pass null in there, because that's not how this feature is supposed to work. So it goes for all the others as well, right? For Java, of course, it's a bit worse because, well, it doesn't know about this, so it will allow it and then fail at runtime. Although we'll see in a moment there's some other ways you can avoid it. And the answer how they do this is pretty much this right here. So at every class that the Kotlin compiler produces, every class file, they compile in this annotation right here called metadata. What we find in there is first MV, this is metadata version, so this is just the compiler version 160, some checksum that we don't really care about, and then we have D1 and D2. These are the interesting ones, the interesting fields. So D1 being data 1, D2 data 2, and what this is essentially is in D2 you have sort of pointers to things in the class that this sits on top of, and in D1 you can see it's not human readable, it's just code points, sort of markers. So what this would tell us in this case, although we cannot really read it, and it's also not really well documented, is that we have a class called nullability, and it has a field number, and that is of type java/lang/number. And then somewhere in this unreadable D1, it would sort of have some marker of being like, this field with this type uses the Kotlin feature non-nullable type, or is supposed to do that, right? And you see I cropped it off at the side, so this goes, the D1 goes on for very, very long, and this is just for this short, stupid class. So typically, this is quite some code that it adds because of this. So what happens then, if we go back to the example from the previous slide, is that you can actually not disable this feature in the Kotlin compiler, and you will see in a second why that is. So if we get a Kotlin library in this example as a jar being the bytecode, it always will have these metadata annotations everywhere. You cannot not have it. And then what it does, of course, is if you, as some probably already expected, it obviously first will read the bytecode. So I would call stuff out of the library in my own application to make sure of obvious things that just sort of are JVM stuff. Again, type system and so on, right? I want a number, I cannot pass a Boolean or something. But the other thing it does, it would read out this metadata annotations such that it can make sure that the features work correctly. So in this case, it would read, oh, this field is supposed to use Kotlin feature non-nullable type. I'm not exactly sure how they modeled it, again, because it's not super well documented, because it's pretty sort of internal to the Kotlin compiler. But it would then read that, see, oh, this is supposed to be non-nullable type. Thus, if I would sort of call this library constructor with null, the front end of the compiler fails, gives me a nice error message, and I never even make it to runtime, which of course is what you want. Otherwise, if you think about it, if they wouldn't have such a mechanism, Kotlin running on a JVM would be pretty useless, because like half the features you sort of would get runtime errors, which is obviously not what anyone wants to have. In Java, if you call it from there, it's a bit worse, of course. So what will happen here, obviously, it will just read the bytecode, right? The cool, or the thing, as you know, for annotations is they're entirely optional, right? So the Java compiler, in this case, will see it and be like, I don't know, no metadata annotation, and just ignores it. So that's precisely why they add these synthetic extra checks in there. So if you happen to get there somehow, typically by using it from another JVM language that's not Kotlin, at least it fails fast. And then this is, of course, also how, if you ever used any Kotlin library, how you get this. So you have a stupid example, a Kotlin library that returns a random string, in this case a non-nullable string. But if I do the same, if you've ever used any Java library from Kotlin, at least by default, it defaults to being everything nullable. So it always wants, or infers at least, that everything has a question mark behind the type declaration. Because it cannot know, right? Everything is nullable, so it just assumes that. But then the cool thing here is if I would now combine this together in a collection of non-nullable strings, I make a list of these two strings, yes, it would fail in the front end precisely because it knows, no, string and string question mark, they're separate types for me, so that's not according to language spec, so I fail. If we then look at this running or using some sort of IDE, right, or editor, it gets a bit better. So IntelliJ by default ships with the Kotlin plugin, unsurprisingly, given that both are by JetBrains. And the plugin, or the screenshot you saw on the previous slide is, as you probably noticed, from IntelliJ. So what they do there is they also just read the metadata. So actually this plugin, of course, has to do quite a lot of stuff that later the compiler frontend would anyways do again, such that you, instead of starting to compile and then get the error message, you get the nice squiggly line. That's the reason why most people use an IDE, I guess, that it tells you beforehand before you even have to start compiling. On the Java plugin of IntelliJ is a bit better because they do read these generic annotations at least. So the stuff you saw previously with the not null, for instance. There are a few of these that the Kotlin compiler adds, but honestly it's only for like sort of the most common features. Most of them do not have that. So in this case, at least then we would sort of get the same. The compiler, the plugin or IntelliJ will squiggly line be like, yeah, you can give null to this constructor. It will also compile, but then I'll warn you, it will fail at runtime. You get, obviously, one of the big reasons why people use IDEs, a bit of a better experience. This is not per se married to IntelliJ. These things are just in the bytecode. So I haven't checked, but I presume VS Code Java plugin might also use them. Last time I checked, it's not that easy to find out, but last time I checked, the Java plugin actually did not use the metadata annotations, weirdly, even though they could do that, I guess, because then, yeah, you could have even more Kotlin features checked at sort of development time before you even start compiling anything. Right, you now only saw one of the examples, which is good so far, but of course I looked at almost 40 other ones. So what we'll do now is I prepared a more in-depth slide to look at slides, plural, to look at other things. So if you scan this QR code or go to the website and enter this ID right here, you should be able to vote which ones we want to do, and then for the remainder of the time we'll do the 1, 2, 3 top most voted ones in more detail. So I'll give you some seconds for that, and then if you don't know some of these features, I will quickly explain at the beginning, like in one sentence, what it does. So no one is completely lost, but yeah. All right, let's wait another few seconds. All right, let's start, I guess, then with operator overloading, since that has the most votes. It's one of the more basic ones, actually, but nevertheless. Well, it's okay. So what you can do in Kotlin, in case you're not aware, is you can overload some of the operators. So like here, I have a class that is sort of a vector of sorts, a velocity in this case, and you can overload some of the, in this case, multiplication sign to do whatever you want, some custom functionality. The way this works is I say, or you have to say, operate. It's an operator fun, so there's a keyword as well. And then based on the method signature, in this case, times is sort of mapped to be multiplication sign. You can do whatever the hell you want. And then you see in the call side here, which can be more expressive, although this is a bit of a dangerous feature, honestly. It can be more expressive because you can now say velocity times 2, and sort of internally it does whatever for this class times 2 means. How this works then under the hood, or what the Kotlin compiler does here is, as I warned you already, not that impressive, but still interesting to look at. So in this case, so the first thing you note is on the left-hand side, this data class was sort of exploded to like a POJO of sorts, unsurprisingly. And the other thing you notice, it just compiles in this times method right here. Actually, the signature even, of course, matches entirely. So it has to be called times. It has to accept an integer. The argument name doesn't matter, but the rest does. And then internally, so to say, it just when in Kotlin you do this nice ×2 thing, it just invokes this method. So this is, as I said, nothing super fancy. But the other thing, of course, that this allows for is that this API is still sort of usable, at least from other JVM languages. So I cannot in Java couldn't do it with the operated overloaded operator, but you can still do .times and then give it some integer, and it would just work fine. So this is a pretty clear example of where the compiler backend does most of the work. So it sort of adds this method and calls it behind the scenes, even though you never actively invoke it. Right. Let's see. The next one is named argument. You choose all the boring ones. What's going on? Yes. So what you can do, this quite some languages have. I guess Python being the most obvious one. You can pass arguments in different orders. So you can see here I first accept query string and then start Boolean, but I pass them the other way around. And the other thing you can do is you can have default arguments. So you see the Boolean by default is false, but I pass it as true, right? Yes, how this works under the hood is something like this. I hope it's actually quite large, nice. Cool. So you see that the first thing it does here is it adds sort of two methods. So we have our prepare search, which expects takes the arguments, and then what you notice actually, that's quite funny. When I saw this, I was like, come on, this is really how they do this. They just sort of order them in the correct order again. So during the compilation, hiddenly, it just sort of, even though you give it custom order, it just orders it in the order that your method wants it, and then just compiles that into the bytecode. So this is a very simple fix, I guess. So you see in the call side, whereas I called it with first Boolean then string, it's actually now string and then Boolean, which is precisely the order that the method wants. And then the other thing that you notice is that it added this prepare search $default, which is for the default Boolean that I gave it. So you see here, this is one of the examples where the decompiler, sort of the step from the bytecode into the decompiler, adds some stuff that's a bit funky. So the sort of hard codes with this if statement, the hard codes in air quotes, the Boolean to be false, because this is what I chose as the default argument. And then it just, forwards the call to my other method, so it's overloading of sorts. To avoid some weird clashes, what they also do is they add this object and just hardcore pass it as always null. So they have this default constructor marker, as they call it, to avoid that you have some weird clashes with somebody that happens to have the same name for whatever reason. Yeah. Another thing you notice here is that this is actually from CFR, this decompiler I used. I didn't add these. It does add these synthetic keyword, which is obviously not a keyword in Java, to show which methods sort of were not present beforehand. Right. Oh, wait, is this? Let's check if this is actually the next one. Reified keyword. That's a very interesting one. Good choice. Yes. So the reified keyword. So what you can do in Kotlin to any method that uses generics, parameterized types, you can say here that my t, so this is an extension function that I can invoke on anything, any generic t, that is reified. So what this means is that it sort of tries to circumvent type erasure to have access to, the type, whatever this was called on, at runtime. So this is keyword here. The other thing you note though is, which is very important for how this works, is the inline keyword. And actually the compiler, if you add reified anywhere, if you've ever tried that, it forces you to add this inline keyword here. So if you don't have it, it won't even compile in the first place. A very good reason for that. Because if you look at how this is implemented, so maybe we should have first looked at the inline keyword now that I think about it, but we can still do that, is something like this. So you have, at the bottom is the method that I implemented. You here actually also, without me wanting to, you see how it implemented extension functions by just sort of calling it as another function. It's not that impressive. But what you notice is that the method at the bottom is actually completely unused. They leave it in there, I guess, so you can still call it from like another JVM language, not quite sure. But the method itself is unused. But then the other thing you notice is that it completely inlines, hence the reason why you need the inline keyword. the entire method to each of the call sides. So here you see from the previous slide the actual thing I did, class.supertypes. That's internally calling reflection.get or create Kotlin class, and then the class, and then calls to get supertypes on that. So you see it sort of copied, or well, inlined the whole piece into my call side. And then it just hard codes whatever at that call side the T is, in place here, so we do not lose it during compilation phase. So that would mean that if I now have this, I call this in like 20 different places, it just sort of inlines it at all the 20 places to circumvent the type erasure. So this I found pretty clever. Let's see. Inline keyword, yeah, okay. I mean, there's not that much to explain because you already saw the other example, but let's do it anyways. Actually, there's a good example here. So here I'm using these scope functions also in apply, which internally look something like this. If you're not aware of at all what that is, yeah, I think that takes a bit too long to explain now. There's actually a video on the YouTube channel about this, so you can check that out. But there's this inline keyword you see here that they added. So this is from the Kotlin standard library. This is not something I wrote. So what you can do is you can call this on anything and then do some sort of side effect, right? And it has the inline keyword right here. And then, I guess unsurprisingly by now, what this looks like is that it just sort of shoves all the code that we did with the also and the apply into the call side right here. The reason, of course, that they do that is because otherwise you every time would add stuff to the stack frame, another frame to the call stack. So in this case, it's now all in line, and you sort of never actually invoke the also and apply methods. They're never invoked really. This is one example again where this looks like no one would write it like this, I hope, but this is what the decompiler spits out at the end. Right, let's see another one. I'm a bit fast. Usually this takes like a lot longer, so I think let's do maybe one or two last ones. Iterating over range, okay. Where is it? Here we go. So what you can do, the first thing many languages have, so just like a range of numbers. The other cool thing though that you can also do in Kotlin is to have a progression, which has something like, you can see here, 100 down to 0 with a step of 5, which is a bit more powerful in some cases at least. And this is actually also a pretty cool one, how this is converted. So what it does here, mostly for performance reasons, is that it actually completely ignores the progression and the range types that do exist, and just compiles this into boring old do-while loops. So the range in here, we start with the starting point, and then it's just a do-while that increments every time until we reach our endpoint. With the added bonus, of course, this is just, even using primitives, just a do-while loop, right? So no extra objects created and whatnot. So this is a pretty nice one. And then the progression is a bit weirder looking because you can do it in like different directions, and also you can have these different steps. And even if your arguments are sort of variable, they first check if you have to iterate at all, and only then start iterating. It does it interestingly a bit differently. So in this case, it decrements, but then checks until the two values, the start and end point, are like not the same anymore. But in essence, this is how this looks like. Right, let's do one last one, and then top level function. Also a nice one. Yes, what you can do in Kotlin is, I guess, so it's a bit more sort of scripty, is you can have functions straight in a .kt file, no class around it, nothing. You can even have fields directly in there, or variables in this case, I guess. I said field for a good reason, as you see in the next slide. On the one hand, this is maybe a bit of an obvious one, but there's also another interesting aspect to it. So the obvious thing is it adds a class around it, right? Because it has to. There's no other way to do this in JVM Bytecode. The name it uses here is the name of the file, and the .kt stripped off. So I named this top-level function, and that's sort of how it infers the class name. But then it has to, of course, do in the background all sorts of linking, such that when I then use this from Kotlin, it's still, I never actually see the class and the method calls and all sorts of stuff. So the interesting thing that you see here is that this variable that I have, what I call mutable state, is a private static field, which sort of makes sense because you can override or read out of this field from other .kt files just fine. So of course it has to be static because, well, of this file I can only have I cannot like instantiate the file twice. So the field is static, and instead they have a getter and a setter to sort of override it. So that would mean that in Kotlin then I can just have regular variable assignment, can just say mutable state is now with equals operator equal to 10 or something, and internally it calls the setter. The circumference method is as expected, and the other interesting thing that you notice here, which you might have seen in a few slides already, is that it also synthetically adds this the dreaded public static void main with the string array as the arguments, which is not required in Kotlin. So it just compiles this in because it has to, required, and then it just forwards the call to the other one that accepts no arguments. Either works in Kotlin. So to summarize, what you'll notice with most of them is that either they use the compiler frontend to get their feature to work and be verified to work correctly, or the backend. Although you'll see that most actually use a combination of both. Some rely stronger on the one, some stronger on the other. And the other obvious thing that you notice, of course, is that the nice thing about this is that in Kotlin you have a lot of things that look very nice and expressive, and the compiler actually hides a lot of the ugly reality of how this has to be working on the JVM, well, under the hood, which is cool for the programmer. Right, then to round this off, before you go, I showed you a few of those now, but of course there's all the other ones that I analyzed. So the link is very tiny maybe, so take a screenshot, a photo if you want to. I created a public repository on GitHub which contains all of the other examples that I did. So you'll find in there the Kotlin original snippet as well as the decompiled Java, and you can also very easily get the class file if you really want to look at the bytecode yourself. So if you're interested in this, check it out. There's a lot of others. I cherry-picked a few, but there's others that are also really interesting. This worked really well for all of the ones you saw on the slide initially. Again, apart from the sealed, not the sealed interface, the suspend keyword, which the decompile just exploded on. It couldn't handle that. But yeah, check it out if you want to. And apart from that, thanks a lot for attending. You can follow me on Twitter if you want to. You'll also there find the link to the YouTube channel, which again is a bit hard to find. And otherwise, again, come to the picnic booth or our vehicle if you want to know more about what we're doing, or if you're looking for a job. And apart from that, thanks for attending, and I see you around.